Module 3 is concerning decay and environment. More specifically, we will deal with phenomena and mechanisms of decay. This is a highlight to what is happening at the interface between materials and environment, with a final result, the deterioration. That means the diminishing of all physical, chemical, mechanical properties and microstructural properties of materials. Major decay mechanisms such as physical, chemical, biological, mechanical mechanisms of decay are developing major problems related with the pathology of structures. These are triggered by atmospheric pollution, by salt crystallization, by water transport within the microstructure of materials, and biological activity. The final output is examined as well. The decay phenomena are defined by the degradation over time of the material's properties leading to failure. They are classified according to the mechanism as mechanical or physical decay phenomena, chemical decay phenomena, biological decay phenomena, which are developed at the interfaces of materials and environment, or materials and materials as a function of intrinsic and extrinsic factors. Intrinsic decay factors are related to materials' properties. It is in function of the type of building materials. There might be stones, mortars, ceramics, glasses, metal, wood, or advanced materials. They are related to whole the set of building material properties, mineralogical properties, physical, physico-chemical, chemical, mechanical properties, and they are determined by the mass distribution at macro and micro scale, this meaning the microstructure of materials. Materials are diversified against their provenance or processing technology, the techniques and production technology, and of course their history. Their history in construction, repairs, maintenance, reconstruction, which is determining, among others, the compatibility of the new conservation materials to the historic ones. Extrinsic decay factors are concerning general climate characteristics like distribution, orientation, or amplitude of environmental factors, relative humidity, temperature, wind direction, microclimatic factors like the orientation and the morphology of the surface, mainly regarding the attack by the rain, atmospheric pollution or marine environment, water attack by all means, aerosol, rain, rising damp, condensation, salt crystallization, biologic factors regarding fauna and flora, usage of buildings regarding external or internal environment, and the in-between, that means the building environment, and the mechanical loadings which are transported from the environment to the structure through temperature fluctuations, expansion of metal braces, salt crystallization, frost, seismic vibration, and abrasion. Our approach to the study of decay is bridging macro to micro scale. Macro scale as decay patterns, the morphology of decay. Microscale as the kinetics of the phenomenon and the thermodynamics of the phenomenon. This meaning the susceptibility of materials to decay. Up to date, the decay was correlated to the external material surface. Today, our knowledge is obliging us to understand the decay correlated to the damage. That means materials and structures are interrelated. As we might see here, concerning the data from granite monuments around Europe, the modulus of elasticity is diminishing, is degraded, as far as the mineralogical quality of the material is diminishing. That means as far as we have decay, we have damage. Surface decay patterns are related to the air pollution or the marine atmosphere attacking to the material surface. Granular disintegration and detachment is the output, and as we can see here in the sanctuary of Demeter in Eleusis in Greece, the marble surfaces are suffering from a sugaring phenomenon, which is observed in the scanning electron microscope as open microstructures evidenced with subefflorescence of gypsum. This is proved by electron probe microanalysis to be a chemical result as well. Regarding the surfaces that are oriented to the rain attack, washed out phenomena are occurring, as we might see in the sanctuary of Eleusis as well, and which are observed as intercrystalline decohesion in the scanning electron microscopy, where the crystals of calcite are covered by various particle formations, as confirmed chemically by the electron probe microanalysis. This phenomenon of washing out is occurring mainly to the direction that the rainwater is washing the marble surfaces, attacking, dissolving with the presence of the acid rain, the marble surface, and developing, dissolving materials from marble or calcite. These materials are recrystallizing at the surface in a way that we have these very clean white washed out surfaces. Carbonate crusts are usually white. Black crusts are the crusts of formation of gypsum. As far as a polluted atmosphere is present, we have the reaction of the various sulfates on the surface with the marble, which are developing gypsum formation. The very well known needles of gypsum crystals are observed in the scanning electron microscopy and are chemically confirmed by the electron probe microanalysis nearby. What is obvious is that we might have, and we usually have, we mainly have this crystal formation of gypsum on sheltered surfaces. That means where the water is not washing out the marble surface. This is the reason that various carbon aggregates might cover and give the black color to the gypsum crystals. This is the reason that we usually refer to black crusts. We have black-gray crusts. These are very well adhered crusts at the outer surface of the material, and they are occurring when we actually have some very low, at a zero velocity, raining, washing of the marble surface by the rainwater, which is permitting, due to these very low velocities of the exchanges, a dissolving and recrystallization of calcite, either of marble or of other calcitic stones, in a way that below of the outer surface of the recrystallized calcite, there might be sheltered various amorphous formations or gypsum crystals. This is the reason that we have the black-gray color and a very well adhered external crust. In the case that we have rusty yellow patinas, the same phenomenon occurs, but including instead of other amorphous materials, the attack of various metals like ferrous ferric oxides, aluminum, cuprum, titanium, and others, which are impregnating the marble surface and which are giving the rusty yellow color to the patina. Of course, in the case of Eleusis, which is surrounded by cement industries, we are having the fingerprint of these industries in the form of cementitious crusts. The cementitious crusts are formed by the amorphous alkali silicate depositions, which are reacting, as we see in the scanning electron microscope, developing a very coherent crust of cement, and this is confirmed by the chemical microanalysis in the graph nearby. This phenomenon is developing on the horizontal surfaces because the cement dust can react only in the presence of a lot of water, where the rainwater becomes stagnant and it is reacting to give the cement products and the cementitious crust. The cementitious crust is exerting mechanical pressures due to the hydration phenomena to the marble, and that is the mechanism of pitting of the marble. Of course, these phenomena of decay patterns are related to other alterations which are happening on the surface. But the most important is that phenomena of crust formations are related to weakening or failure. That means to damage not only at the external surface of the materials, but in depth. For instance, relating the phenomena of gypsum formation at the outer surface of the sculptures of caryatid statues. We might see that after washing out and dissolution of the gypsum, we are losing the sculptured areas of the face, of the hairs, or even of what is the whole statue of the caryatids. This is a phenomenon which is continuously repeated with a final output, the disappearance of the sculpture. The reason of this continued effect is the one that led caryatids to be protected within the Museum of Acropolis, and is concluded with replicas on site. Gypsum formation, of course, according to the mechanism which is studied by Professor Skoulikidis, is a phenomenon that might occur even in dry. It might occur in a way that more or less an electrochemical potential is developed on the marble of surface, and the phenomenon is feasible even without water. Other crust phenomena, like the hard carbonate crusts, which are developed by acid rain dissolution and recrystallization at the outer surface of calcite, are followed by the masonry collapses we might see here in the masonry structures of Contrascarpa, of the fortification of the medieval city of Rhodes. These are phenomena that can occur because even though the recrystallized calcite at its outer surface is very hard when we try to measure its hardness, inwards, due to the calcite migration to the outer surface, we have a very fragile material. It is so fragile that when we exert stresses, like in the case of Contrascarpa, we might have a failure of the masonry structure. Of course, the phenomena of dissolution of weak acids are followed, as I said, by recrystallization. But this is not saving the material from decay and collapse. Salt crystallization, on the contrary, is more selective. As we might see here, in the case of the Venetian fortifications of Heraklion in the island of Crete, we have selected disaggregation on a certain level of the height of the masonry. This is related, as we might see, regarding the total soluble salts, at the level where we have the maximum of total soluble salts and where the maximum of porosity is occurring. This is identified to the height where we have the maximum of the evaporation processes. That means if we have capillary rise of humidity which is augmenting, we have at the same time from the upper height augmenting phenomena of evaporation. At the level of equilibrium, we have the maximum of total soluble salts, and the maximum of decay. This is explained by the fact that where the salts are crystallized, there we have disaggregation of the stone material. Of course, at the same area, we can see that there is diversified the pore structure of the material with augmenting porous radii which are related to the disaggregation area. The role of water of decay is decisive, with many sources of moisture, through ground moisture, which is rising damp, through condensation, through rain, through accidental actions, that means through very diversified humidity sources. We have interaction of water with building materials. Water is rising through the pore structure, which is a chaotic structure with channels that are connecting the outer environment to the inner material, or with dead ends, ink homes, or telescopes that are stagnating the water within the material structure, or even closed pores. However, the water is carrying soluble salts, and this is the main reason that water is inferring decay. Not only because it might alternate, for instance, soluble stones, like the ones that are consisting of argillaceous minerals, but mainly because in the case of insoluble stones like the calcitic ones, it might, within the cycles of drying due to the evaporation of the environment, develop salt crystallization, which is deteriorating and damaging materials and structures. In the question why should salt crystallization develop collapse mechanisms within the masonry, we can answer with these images. In the medieval city of Rhodes again, we can see that the salt crystallized within the very porous calcitic stones is disaggregating, disrupting the material when the tension is overpassing the strength of the stone, and is developing this honeycomb structure of the materials. This honeycomb structure is related to the diminishing of the outer surface towards the inner one. When the the stones underneath are diminishing their outer front, that means that they cannot bear the sitting stones, and due to this disequilibrium, we have a collapse mechanism in the masonry. Salts are crystallizing when evaporation phenomena occur, and when we are having relative humidity in equilibrium with saturated solutions that are over-exceeding the relative humidity of the pore. Of course, we need to have a supersaturated solution. Under these conditions, we have the development of salt crystals in the pore, which are starting from the larger pores to the smaller ones, developing strong possibilities for fracturing the pore walls at the intersections of small to larger pores. The evaporation zones are developing columnar crystal growth, while at the inner of the material we have the well-cubic crystals, which are in equilibrium with the supersaturated salt solutions within the pore. The decay model due to salt crystallization regarding this porous calcitic stone of biocalcarenite is presented here when the columnar development of the salt crystals is over-exceeding the strength of the material. We have granular disintegration of the porous stone. Not only the stones, but the mortars as well are dissolving and are damaged by salt decay. This is the reason that when in rubble masonry mortars, like in the case of the Contra Scarpa in the medieval city of Rhodes, we have mortar deterioration, we have a collapse masonry, collapse mechanism of the masonry as well. It is starting from nearby the ground position, and it is going upwards. So when the underneath layers of the masonry cannot bear the the upper layers, then they are collapsing. Incompatible materials are the ones that, as in the first photo, in the case of the Debeki restoration with cement concrete mortars around the very porous biocalcarenite stone of the medieval city of Rhodes, are giving, after digital image processing, the image of very disaggregated material, where we have dark colors, violet, blue, black colors. This is related to the depth of the cavities which are developed by materials disaggregation. On the contrary, where we have the yellow color, this is the color mainly related to the very strong and cohesive cement or the salt efflorescence developing at the areas, at the surface areas. The reason of the fact that cement concrete is actually corroding, is eating to such a cavity the stone, is that cement concrete is not absorbing water. It is more or less orienting the water and accelerating salt crystallization in the more porous and friable stone. That is the reason that cement concrete is acting as an accelerator of deterioration and decay of the original historic material. This is incompatibility. Incompatibility means the absolutely diversified way that two materials are acting against the environment, and the fact that the more advanced materials with less porous structure are corroding the more porous historic materials. This is the main reason of incompatibility. The same phenomenon is occurring in the third photo, where we have substituted all the porous stones by more dense stones in order to repair the meson. This physical photo is digitally processed and is giving the image of the very dense porous stone by yellow, and the original ones by the more coffee Bordeaux colors with blue and black as the points of accelerated corrosion. We might observe around the yellow surfaces blue and black, which are appearing in a very dense appearance in relevance to the original surface. That meaning that we have acceleration of decay at the interface of new to old material. Of course, mechanical factors are very important, not only temperature fluctuations, which at a critical and dramatic case might be shown by the explosion of Parthenon due to the Morosini invasion in Athens, as drawn by Manolis Kores, but they might be exerted by metal joints. Here we have another dramatic phenomenon, a fracture of marble due to weathering of the metal joints inserted by the Balanos restoration 1912 in the Acropolis of Athens. Professor Skoulikidis has allocated this phenomenon, has studied where the metal joints were inserted, and has substituted iron metal joints by titanium. Decay of mechanical factors, apart from soil decay, which is actually of the same mechanism, is the frost decay. When water becomes frost and expanding, is disaggregating the stone. Seismic vibrations are critical for sustainability of historic structures, as we might see in Daphne Monastery, or here in the study of seismic vibration and the response of Hagia Sophia in Istanbul. We can estimate in the fragility curves that ground accelerations, which are developing a monument model response to them, are dealing with material properties. The modulus of elasticity of the materials is defining the level of damage and the possibility of damage. We could have large, medium, or small damage related to a certain ground acceleration for different modulus of elasticity. The biological factors are acting in the same way that chemical reactions or sometimes physical reactions are occurring at the surface of the materials. And as we can see here in the tessera of mosaics in Delos, or the stone masonry structure of medieval fortifications of Rhodes, we are having deterioration of stone due to the acid deposition of the biological activities or due to the physical corrosion, which is diversifying the microstructure of the stone.